Good morning, dear students. In today's topic, we are going to study about vector field on surfaces, its orientation. So, vector field എന്ന് പറയുമ്പോൾ, do you know what is a vector field? Vector field is a collection of vectors on surface, and so we are going to deal with certain types of vector field. So first we have the definition of vector field, x bar. X bar, capital X bar is a notation for vector field. A vector field x bar on an n surface S is a function which assigns to each point P in S a vector x bar of P at P. So basically, vector field x bar എന്ന് പറയുന്നത് അതൊരു function ആണ്. It's a function from the surface S to surface S. It is a function on the surface S such that at every point on the surface we can assign a vector at that point. Simply we know vector field is a collection of vectors. So at every point of P, if we can assign a vector at that point, that collection of vectors we call it as vector field. So remember, the notation of vector field is capital X bar. The notation of a vector is x bar of P. If x bar of P is a tangent vector, so if at every point, if we can assign a tangent vector, we call it as a tangent vector field. Then x bar is said to be a tangent vector field on S. Similarly, if x bar of P is orthogonal, that means it's a normal. If we are considering normal vector at each point on S, we call it as a normal vector field. So we are having, we know we can consider a surface. So this is a one surface. So at every point, if we can assign a tangent vector, at every point we can see these are tangent vector. This is one surface, this is the one sphere. At every point we can see, a tangent vector at that point. Then collection of such vectors is called as a tangent vector. Similarly, at every point if we assign normal vectors, then we call it as a normal vector field. So normal or orthogonal vectors, okay, then such collection of vector field is called as normal vector field. So in the first figure, we are considering vector fields of all vector field in which at every point the assigned vector is a tangent vector. This is an example of tangent vector field. And if we are considering vectors at every point which are normal, then we get a normal vector. So as usual, we shall work almost exclusively with functions which are smooth. So we are dealing with everything which are smooth. Okay, functions and vector fields which are smooth. There is no question arises, no discussion arises when it is not smooth. We have to consider a vector field which is smooth. So let us see the definition of a smooth function. A function g from S to Rk. When can we say that a function g is smooth? Is smooth if it is a restriction to S of a smooth function, defined on some open set V in Rn plus 1 containing S. So simply speaking, if g is a function and g is said to be smooth, g is a function on S and g is said to be smooth, if g is the restriction of a smooth function g tilde. Okay, g tilde is already a smooth function defined on V, and ഇതിന്റെ ഒരു restriction on g angle, we can say it is g is a smooth function on S. Similarly, a vector field. We know vector field is also a function x bar. And ഇപ്പം പറഞ്ഞ പോലെ തന്നെ ഫംഗ്ഷന്റെ സ്മൂത്ത്നെസ്സിന്റെ അതേ കൺസെപ്റ്റ് ഇവിടെയും വരിക. A vector field x bar on S is smooth if it is a restriction to S of a smooth vector field defined on some open set containing S. So vector field x bar on S is smooth if it is a restriction to S of a smooth vector field defined on some open set. So x bar is smooth if and only if x bar is the function S to Rn plus 1 is smooth. അതായത് we know vector field is equal to x bar of p equal to p comma x of p. ഇവിടെ x എന്ന് പറഞ്ഞാൽ it is a vector, right? It can be a tangent or a normal or any sort of vectors. So if this x is smooth, then we can say capital X bar is vector field X bar is also smooth. Now let us see the theorem 1. So this theorem, the theorem extends to n surface, the theorem of chapter 2. So precisely നമ്മളൊരു existence and uniqueness theorem of integral curves പഠിച്ചായിരുന്നു chapter 2ൽ. അതിൻ്റെ ഒരു എക്സ്റ്റൻഷൻ ആയിട്ട് ഇതിനെ കൺസിഡർ ചെയ്യാം. സോ അവിടെ there we were dealing, so അവിടെ നമ്മുടെ സ്പേസ് വേറെയായിരുന്നു. Here we are dealing with n surface. So let S be an n surface in Rn plus 1. X bar is a smooth vector field. P is a point on S, then there exists an open interval I containing 0 and a parameterized curve alpha such that alpha of 0 is equal to P. Alpha dot of T is equal to X bar of alpha of T. If beta from I tilde to S is any other parameterized curve in S satisfying 1 and 2, then I tilde subset of I and beta of T is equal to alpha of T for all T belong to I. So simply speaking, if S is an n surface and X bar is a smooth vector field on S and let P belongs to S, then there exists an open interval I containing 0 and a parameterized curve alpha from I to S such that alpha of 0 equal to P. That means alpha is the curve passing through the point P. Alpha dot of T equal to X bar of alpha of T for all T belongs to I. If beta from I tilde is any other parameterized curve in S satisfying 1 and 2, then beta of T is equal to alpha of T for all T belong to I tilde. So let us see the proof. So another thing, if there exists such an alpha, ഈ മൂന്ന് കണ്ടീഷൻസ് സാറ്റിസ്ഫൈ ചെയ്യുന്നൊരു ആൽഫ ഉണ്ടെങ്കിൽ ദാറ്റ് ആൽഫ ഈസ് കോൾഡ് ആസ് മാക്സിമൽ ഇൻ്റഗ്രൽ കർവ്. നമുക്കറിയാം ഇക്വേഷൻ നമ്പർ 2 is the definition of integral curve alpha. And maximal integral ഈ മൂന്ന് കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്യുന്നുണ്ടെങ്കിൽ we call alpha is a maximal integral curve of x bar vector. സോ മാക്സിമൽ ഇൻ്റഗ്രൽ കർവ് എന്ന് പറഞ്ഞാൽ അർത്ഥം എന്താണ്? അതിലും വലിയൊരു ഇൻ്റഗ്രൽ കർവ് നമുക്ക് ഫൈൻഡ് ചെയ്യാൻ പറ്റത്തില്ല. മാക്സിമൽ, ദാറ്റ് ഈസ് a term we often use. Maximal means something we cannot find anything greater than that which satisfies these properties. So let us see proof. So since x bar is smooth, there exists an open set V containing S and a smooth vector field x tilde on V such that x tilde of P equal to x tilde of Q equal to x tilde of x of Q for all Q belongs to S. So we know capital X bar is smooth. There exists an open, so X bar is smooth ആണെന്നറിയാം. By definition of smooth vector field we know that X bar സ്മൂത്ത് ആണെങ്കിൽ എക്സ് ബാർ എന്ന് പറഞ്ഞാൽ ഒരു സ്മൂത്ത് വെക്റ്റർ ഫീൽഡിൻ്റെ ഒരു സബ്സെറ്റ് ആയിരിക്കും. സ്മൂത്ത് വെക്റ്റർ ഫീൽഡിൻ്റെ ഒരു റെസ്ട്രിക്ഷൻ ആയിരിക്കും. Where x tilde is defined on V, then this is the definition of restriction function. Okay, capital X bar ഒരു restriction function ആണെന്ന് കാണിക്കാനായിട്ടുള്ള ഒരു ഡെഫിനിഷനാണ്. For all P Q belongs to S. Let F belongs F from U to R and C belongs to R be such that capital S is equal to F inverse of C and tilde and nabla F of Q not equal to 0 for all Q belongs to S. So we consider F from U to R is a function and C belongs to R is a constant. S is equal to F inverse of C. So this is basically the definition of the surface. S is equal to F inverse of E, where F is a function from this to this, satisfying this condition. Now we are going to consider a set W equal to set of all Q belonging to U intersection V such that nabla F of Q not equal to 0. So we can see that W is equal to set of all Q belonging to U intersection V. So that means W is equal to u. We know what is u. U എന്ന് പറഞ്ഞാൽ എന്താ? U is the open set, right? U is the domain of F. And V and the V is the domain of X tilde. So U intersection V both are open, right? U and V open. A finite intersection of open set is open. So W is an open set, okay, containing S. W is an open set containing S. And both X tilde and F are defined on W. നമുക്കറിയാം X tilde domain ആണ് V, F in the domain U. So X tilde and F are defined on W because running domain the intersection on W. Let capital Y be the vector field on W. So let capital Y be the vector field on W. Everywhere tangent to the level set of F defined by Y tilde of Q is equal to X tilde of Q minus X tilde of Q dot nabla F of Q by norm of nabla F of Q square into nabla F of Q. So we have defined a new vector field Y of Q, which is in terms of X tilde terms, Y vector field Y നമ്മൾ define ചെയ്യുന്നു. സോ നമുക്കറിയാവുന്ന ഒരു കാര്യം എക്സ് ടിൽഡ എന്ന് പറഞ്ഞാൽ എക്സ് എന്ന് പറഞ്ഞാൽ ക്യാപിറ്റൽ എക്സ് എന്ന് പറഞ്ഞാൽ എക്സ് ടിൽഡയുടെ ഒരു കോഡൊമൈൻ ആണ്. സോറി, എക്സ് ടിൽഡയുടെ ഒരു റെസ്ട്രിക്ഷൻ ആണ്. Capital X is the restriction of X tilde. So, okay, so we know that, now note that y bar of Q equal to X bar of Q for all Q belongs to S. കാരണം എന്താണ്? X tilde എന്ന് പറഞ്ഞാൽ എക്സിൻ്റെ ഒരു ലാർജർ ആയിട്ടുള്ള ഒരു ഫംഗ്ഷനാണ്. അതായത് എക്സ് ഈസ് എ റെസ്ട്രിക്ഷൻ ഓഫ് എക്സ് ടിൽഡ്, യു നോ ദാറ്റ്. അപ്പോൾ ക്യൂ ബിലോങ്സ് ടു, നമ്മളിവിടെ ക്യൂവിനെ നമ്മൾ എസ്സിലേക്ക് റെസ്ട്രിക്റ്റ് ചെയ്യുമ്പോൾ എക്സ് ടിൽഡ് എന്തായിരിക്കും? എക്സ് ടിൽഡ് വിൽ ബിക്കം എക്സ് ഓഫ് ക്യൂ ബിക്കോസ് എക്സ് ഈസ് എ റെസ്ട്രിക്ഷൻ ഓഫ് എക്സ് ടിൽഡ്. വെൻ ക്യൂ ബിലോങ്സ് ടു എസ്, എക്സ് ടിൽഡ് വിൽ ബിക്കം എക്സ് ഓഫ് ക്യൂ. Another. Next, when you are looking here, ഇവിടെ എന്തായിരിക്കും? എക്സ് ഓഫ് ക്യൂ. ദിസ് വിൽ ബി അഗെയിൻ എക്സ് ഓഫ് ക്യൂ ഡോട്ട് നാബ്ല എഫ് ഓഫ് ക്യൂ ഡിവൈഡഡ് ബൈ നോം ഓഫ് നാബ്ല എഫ് ഓഫ് ക്യൂ സ്ക്വയർ നാബ്ല എഫ് ഓഫ് ക്യൂ. ആൻഡ് അനദർ തിങ് വി നോ ദാറ്റ് നാബ്ല എഫ് ഓഫ് ക്യൂ എന്ന് പറഞ്ഞാൽ എന്താണ്? എപ്പോഴും നാബ്ല എഫ് ഓഫ് ക്യൂ എന്ന് പറയുമ്പോൾ ഒരു സർഫസിന് പെർപെൻഡിക്കുലർ ആയിട്ട് വരുന്ന വെക്ടറിനെയാണ് നാബ്ല എഫ് ഓഫ് ക്യൂ എന്ന് പറയുക. ഇറ്റ് ഈസ് എ നോർമൽ വെക്ടർ ടു അവർ സർഫസ്. ആൻഡ് എക്സ് ഓഫ് ക്യൂ, if Q belongs to S എന്ന് പറയുമ്പോൾ it is a vector field. X of Q is a smooth vector field and nabla F of Q will be normal to the smooth vector field. So the dot product will become 0. So y bar of Q equal to X of Q. Let alpha belongs to I from I to W be the maximal integral curve of Y through P. Let alpha from I to W be a maximal integral curve. So we are going to assume alpha as a maximal integral curve of Y vector field Y through P. Then, so consider F composition alpha dash of T. F composition alpha dash of T എന്ന് പറയുമ്പോൾ nabla F of alpha T dot alpha dot of T. So nabla F of alpha of T and alpha dot of T എന്ന് പറയുമ്പോൾ that is y bar of alpha of T because we have assumed alpha as a maximal integral curve of y bar. Okay, so alpha can be written as alpha dot of T can be written as y bar of alpha of T, and so we know y bar is defined on W and W is a subset of S. So we can see that, sorry, the W contains S. So alpha from I to W means alpha actually maps from I to S also. So we know y bar of alpha of T dot this is equal to 0. So this is equal to 0. So f composition alpha dash of t equal to 0 എന്ന് പറയുന്നത് ഡെറിവേറ്റീവ് 0 ആണ്. ഡെറിവേറ്റീവ് 0 എന്ന് പറയുമ്പോൾ f composition alpha of t എന്താണ്? Alpha of t ഒരു കോൺസ്റ്റന്റ് ആയിരിക്കും. f composition alpha of t will be a constant. If you are putting t equal to 0, we get f composition alpha of 0 is equal to constant. Now f composition f of alpha of 0. This can be written as f of alpha of 0. Alpha of 0 എന്ന് പറഞ്ഞാൽ p ആണ്. So f of p is equal to c. So you get f composition alpha of t is equal to c for all t belong to I. So condition 1 and 2 are clearly satisfied, and condition 3 is satisfied because any beta belongs to I tilde satisfying 1 and 2 is also an integral curve. So നമ്മൾ already second chapter ചെയ്തതാണ്. Any alpha which satisfies 1 and 2 condition 3 is satisfied. Any beta satisfying 1 and 2 is an integral curve. Okay, integral curve. Therefore, third condition is also satisfied from our theorem of chapter 2. So next let us see a definition. A subset S of Rn plus 1 is said to be connected if every pair P and Q of points in S, there is a continuous mapping from alpha from closed AB to S for some closed interval AB, such that alpha of A equal to P, alpha of B equal to Q. So P and Q, another for every P and Q, we can get a continuous function from this to this, said to be a connected subset. So if we are looking at this, we can see that if we are looking at this line x1, this is a connected set, right? And the connected set on. Now we can say in the first we are having three graphs, right? So first we are having points P and Q. So this will not be a connected set. If they are only points, it is not a connected set. Because we cannot connect these 2 points by any curve which will connect here. So it is not a connected set. Similarly, in the second case, we are having S1. S1 എന്ന് പറയുമ്പോൾ the one sphere. One sphere means it is a circle. Circle എന്ന് പറയുമ്പോൾ any 2 points P and Q, right? We can see that P and Q. P and Q നമുക്ക് connect ചെയ്യാൻ പറ്റും by using a curve. Okay? We should have at least one curve connecting P and Q. Then we can get a curve like this. So this is an example of a connected set. Now another is, it is a circle with interior, S2. The circle with interior. Circle with interior and the variable, we can see if we are taking any two point P and Q, we can connect it by any circle. There are with connected by any curves. So we can connect indefinitely these 2 points by any curve. So this is also a connected set. So this much, let us see in the next class we'll be doing a corollary and continue with this topic.